also more lecture notes and the video recordings of the lectures are being posted as they come. There's a playlist that you can just see, but they're also linked to the individual days. All right, so what we started to talk about last lecture was so-called phase-space representations, which are particularly relevant in quantum optics when these x and p variables represent the quadratures of the oscillation of a quantized mode of the electromagnetic field. And so the phase-space representation can be one way to motivate it or to define a phase-space representation. As we've already seen, we've seen one such example going back to last semester. The so-called Glauber-Sudarshan representation is an example of a phase-space representation. Hopefully today we'll understand the relationship of that to other representations. But the most natural one to define is what's called the Wigner function. And the Wigner function, I think, is most nicely seen as a generalization of the probability densities that we learn about. If we learn about this first, typically we do, or at least used to in quantum mechanics. Thinking in wave mechanics, we think about the wave function, then the probability density of a measurement of the position is psi star psi being the wave function, which is the position representation of the state. From the point of view of a general mixed state, that's the diagonal element of the density operator, which I can also write in this very fancy way as the trace with the projector onto the position eigenvectors, which is, as we showed, the same thing. This projection operator is this delta function, okay? That's to say, it's an operator where the operator x is equal to the eigenvalue x times the identity, okay? Similarly for momentum. And we just define, and we'll understand, we'll talk a little bit more about what this means today, a joint, what we call quasi-probability density or distribution on the phase space, which is a kind of something that looks like a joint probability distribution in position and momentum, which is just the generalization of these guys as the trace of the state with the so-called symmetric delta function, okay? And the symmetric delta function can be written this way using the Fourier transform, that we know that the Fourier transform of delta functions are plane waves, so we can write the symmetric delta function in this way, where we recognize the operator that we're Fourier transform here to be the phase space displacement. So that's equal to the exponential, which displaces me in position and which displaces me in momentum. No. Yes?
And to clarify, would that be an integral over dx1 and dp1?
Oh yeah, sorry. Yeah, it's all messed up all over the place. So this should be dx1 dp1. Sorry. Thank you for noting that. Yeah. Right. So let's just talk then a little bit about the properties of this Wigner function. Okay. first of all, we can see some of those properties by looking at the properties of the symmetric delta function. This operator is Hermitian. We can see that by taking the Hermitian conjugate of this, that will turn the i's to minus i's, but that's still the same delta function, right? Because the imaginary part cancels out when you do that integral. So this operator is Hermitian, but it's not positive. It's not so easy to see that, but it's true. Which is to say that if I were to look at the eigenvalues of this operator, or more generally, I look at this operator, this expectation value can be less than 0. Okay? What that means from this definition is that the Wigner function is positive. I'm sorry, is real. But it's not positive, okay? Or it can be negative, okay? So this is, from the point of view of a joint probability distribution, okay, it's nice that it's a real number because probabilities are real numbers, but this guy, this thing can be negative, which is why this is what's called a quasi-probability distribution. It's a probability distribution has to be some function that's positive. I mean, it's real, but it should also be positive. This can be negative. And the negativity of the Wigner function is a signature of non-classicality. Now, it's a very interesting, in my view, and still poorly understood, in my view, notion of non-classicality. I mean, it's non-classical in the sense that we can't, when the Wigner function is negative, we won't be able to describe certain measurement outcomes in a classically statistical way. Otherwise, if we could, when this is a problem, we could just say, well, there was an X and there was a P, I didn't know what it was. I assign a probability that to both X and P, and that's a totally classical statistical description. But when it's negative, we can't. So that's a sign of non-classicality. It's also a resource in some sense for doing something when the state doesn't satisfy this positivity. But, you know, it's still a question in my mind. Is it a mathematical oddity? Or is it meaningful in any way? What is the meaning of a negative probability? Is it telling us something about the nature of quantum mechanics? It's something that I think has been understudied. Feynman talked about it some himself. It was a way, I mean, there was a little bit of an argument at some point, you know, was entanglement really something different than superposition and, you know, and negative probabilities? Like, well, it's all really just negative probabilities. What the meaning of negative probabilities is, I think, is something to think about a little bit. I mean, what does it mean? Does it have a meaning? Is there something in physics? I mean, in some sense, it's saying that we have to take away the chance of something happening. Is that a physical thing? Does that mean it's something being annihilated? just leave that for you to muse about a bit, or maybe more than a bit for some period of time. Yeah.
Is it still bounded?
Yeah. So actually, it's a good, geez. Kind of depends on how we're going to talk a little bit more about, let me come back to that because I think there's some things I want to say. It depends on how we normalize things. But yes, there can be only this thing can only be so negative and so positive. Oh, so interesting. Let's come back.
Also, it's not positive because it's, like I understand it's not positive implies that it has some negative eigenvalue.
That's right.
So,
Depends on the state. There are some states for which this is always positive.
right. If you just talk about the delta function, it's not operator.
Yeah.
That is not negative, right?
Yeah, to say an operator is negative is to say that it has negative eigenvalues.
Right. Okay. Cool.
That's what it means. Yeah, and or equivalently, that there exist states for which the expectation value is negative. Okay. What else do I want to say? If I look at the integral over x and p of this operator, well, I'm going to get, in that case, a situation where I get a delta function that x1 and p1 is 0, which means that you can easily go through that algebra yourself and show that that is the identity operator. Okay? And so what that implies is that if I look at the integral of the Wigner function over all space, that is equal to the trace of rho. Okay, as we would expect. If it looks like a probability distribution, that is the total probability density integrated over the whole of space, and if it's normalized, that's 1. Okay, so the integral over all space of the Wigner function is the trace of rho, which is the norm of the vector, or the norm of the state, which is 1. All right. What else? Well, one of the very nice properties of the Wigner function is to look at what we call the marginal probability densities. To marginalize a distribution means I have some joint distribution, and I look at just what the probability for one of the variables is irrespective of the other. So if I marginalize over p, what do I get? Well, if I look at this thing, again, marginalizing over p means integrating over p. Well, that will set x1 to 0, which will mean that this will be equal to the trace of rho at the interval over p which is the delta function of x, right? Which is equal to this. So that's the expected probability distribution that we wrote at the top of the board. So this gives me the correct marginal in p, that's in x. If I marginalize over p, I get the appropriate, what we expect for in quantum mechanics for the probability density in x. Yeah?
And so we should keep this in mind on these marginals and looking at these other property distributions, the Q.
Right.
And the obviously don't show us that
Right,
they
well,
have the correct margin.
No, you're foreshadowing, but yes, the answer is yes, it's no.
Yes.
But we'll come back to that. So the Wigner function has this property, and similarly, if I marginalize over x, I get the momentum space wave function squared, or more generally, the probability. So I get the correct marginals. Okay. More generally, I can think about any quadratures I like. I can think about quadratures that are rotated by some theta, right? And I can ask, I can look at the Wigner function as a function of these rotated variables, if I so chose to do so, which is just the trace of rho with the symmetric delta function at the marginal distributions, the rotated quadratures. And similarly, if I marginalize this rotated guy, exactly the same arguments hold. And this is equal to the probability distribution for measuring that quadrature, where, this is just the rotated version of that, right? So what's important, one of the unique features and this is unique, as Cole was alluding to, but we'll talk more about, is that the Wigner function gives the correct marginal probability distributions. And this is actually, as I understand it, what motivated Wigner in his definition of the Wigner function. He wanted some way of writing a joint distribution of x and p such that if I marginalize over p, I got psi star psi, and if I marginalize over x, I get psi tilde star psi. And the way Wigner's expression, given a pure state, was the following. So Wigner wrote down this form originally, sometime in the 1930s. Soon it will be the 2030s, guys.
And yet they still call it modern physics.
Yeah, well, we already had that discussion. You missed that. So this is the same thing as this. It may not look the same, but in fact actually is, and that's one of your homework problems, to show that if you write this in terms of the position representation, this is psi of x, here is the position representation of the state, the wave function, then this is the same thing as this. So what it looks like is a kind of convolution where you displace the wave function in two different psi and psi star in two different directions, and then you take the inverse Fourier transform. Wigner wrote this down this way because it's easy to see that if you marginalize this distribution over x or over p, you get the right thing. Okay, that's how he wrote it down.
I'm sorry, what's y?
Y is a dummy variable.
Oh, okay.
It's just a dummy variable there that we're just integrating over, so that at the end of the day, you have something that's just a function of x and p. But thank you for asking. Good. All right. things we want to say about the Wigner function. There's something called Hudson's theorem. Hudson's theorem says if rho is a pure state, and the Wigner function is everywhere greater than or equal to 0, then this is a Gaussian. Okay. Now that's not an easy theorem to prove, and we're not going to prove it here. But it's a true fact, and it's a statement that says that the only pure states which are everywhere positive are Gaussian functions. We'll see some of those today, but what it means is that non-Gaussianity, don't you love English? You can make anything a word. Is a non-classical resource. Now, one has to be a little bit careful about this, and I've made this mistake myself fairly recently in my own research, because this is only true for pure states. I can have mixed states, which are non-Gaussian, which are everywhere positive. So just because you have something that's not Gaussian doesn't mean that it's a non-classical resource. Yes?
So does this include a convex combination of Gaussians?
Well, that's a mixed state.
Oh,
Okay, so if I have a mixed state, which is a convex combination or a statistical mixture of Gaussians, that can be non-Gaussian and everywhere positive. So it's not an if and only if statement. There can be non-Gaussian states which are everywhere positive. But if it's a pure state, the only pure state that is everywhere positive is a Gaussian. Okay? Yeah?
If we're thinking about states of a mode of the electromagnetic field, if the Wigner function is positive, does rho have to be a coherent state, or can
No.
it be some Gaussian non-coherent state?
Yeah, well, as we will see, it can be a squeeze state.
Okay.
Yeah, yeah. Indeed. Right. You know, it's important to understand also that not every function I can write down is a physical state. There obviously is a constraint on this, including, as it, you know, clearly, for example, if I had a delta function that was localized at a point in phase space, that can't be a physical quantum state, because it would violate the delta x, delta p being less than the bound given by the uncertainty principle. Yeah.
So is there like a steadfast way of determining if a particular Wigner function
Is a physical
corresponds to
state?
a physical
Yeah, whereas we'll see, there's constraints. There's constraints, as we will see, we'll have to, so if I normalize then what we'll see is that we must have that the square of this thing must be greater than or equal to 1, which is an expression of the trace of rho squared. Okay, it's got to be something which is at minimal 1, because that's for a pure state. It could be bigger than 1 for a mixed state. But we know that the trace of rho squared can't be less than 1. And that puts a constraint on the Wigner function. Now, how do we get there? Well, for that, we need to we're going to start on the path of formalism again and remind ourselves of some of the things we talked about last time. And we typically consider complex plane as phase space. Okay, where alpha is our complex amplitude with a real and imaginary part, x and p. Yeah.
Did you mean less than equal to 1?
The purity is less than or equal to 1. Yeah, thank you. I did. Thank you. Okay, so we have our complex phase space. With this our complex amplitude and our complex or non-Hermitian operator, which is the annihilation and then the creation operators, right? And we have the 2D Fourier transform, so 2D functions. So I have a function, a complex function of alpha and alpha star, sometimes written just f of alpha, but it really should be considered a function of f and alpha star. And we get to the Fourier transform, the 2D Fourier transform, f tilde of beta is the integral over the plane with this invariant measure with the pi's because of the way that, we integrate over the plane. Alpha beta star minus alpha star beta f of alpha. I always remember the sign because it's wrong. That's why I know it's wrong.
That's how you remember it.
I remember it in the following way. I just looked at it, no, that's not right. Because the thing on this side, this is the independent variable on the side, then you start with that, beta star minus alpha. That's how I remember it. And then the other way around, so I knew it was wrong, f of alpha is the inverse Fourier transform, which is alpha beta star minus alpha star beta, f tilde beta. Okay, very good.
Today was worth it just for that.
Just for that, now you know how to remember that. Yeah. All right. So with that, we define the symmetric in A and A dagger delta function. Using what's written there. So that is, A minus alpha, A dagger minus alpha star, which is the integral over beta pi squared d beta, maybe I'll write it out, e to the alpha, I'm integrating over beta. Yeah, I think that's right. Beta, A minus beta star minus alpha star beta. It's correct. All right. So this is the equivalent to what we wrote down over here, but in terms of the complex variables. Okay. I define an operator T, which will be equal to pi times the delta function. There are factors of 2 and factors of pi all over the place here, and over the years, I finally think I've gotten them right. Which is defined this way because this is the 2D Fourier transform of the displacement operator. And the displacement operator is the other way. Okay? With that, we had discussed last time the fact that these operators, the displacement operators and the delta functions, form an operator basis, which is to say I can expand any operator as a superposition of these operators weighted by amplitudes that are the projection of the operator onto the basis direction. So, and moreover, what we have is that these operators are themselves, so we define an inner product between two operators through the Hilbert-Schmidt inner product. And what we have is that the inner product between two of these guys is a delta function. They're orthogonal in that sense. With these factors of pi floating around. Moreover, they're complete. You're going to show this for homework. I just quickly say, how in the world would I possibly show that? Well, if I look at this, this is equal to, anyway, the trace of d dagger beta prime with d beta, right? That's the definition of the inner product. How are you going to calculate a trace? Well, I have to take the trace of an operator is the sum over the diagonal dimension, but this is in continuous variables. I could do that in Fock space, but that would be a stupid thing to do. It's better to work with coherent states. So what I can do is I can insert a resolution of the identity, because we all remember that the coherent states form a complete basis. You remember that? Maybe. I think we had it for homework. Maybe. Last semester, didn't we? Yes, we did. And that is then equal to 1 over pi, the integral over alpha that. And that we could do pretty easily, because we know how the displacement operator acts on the coherent states, and then the inner product become Gaussians, and then we take the integral and we do that. Okay. Good. So what this tells us is that they're orthonormal. They're also complete in the sense of, if I look at the operator outer product in superoperator land, it's the identity. It's the same for the displacement operators. What that means, as we were saying, is that I can take any operator and expand it as a superposition of either the delta functions or the displacement operators weighted by the appropriate inner product, which is a trace. I can't move this up, so I'm going to use this word. Made that mistake last lecture. So, with that, I'm going to define what's known as the Weyl symbol, which is the Wigner representation of any operator, as the following. The Weyl symbol for a given operator is going to be projecting that operator onto the symmetric delta function. With a pi. So this was, like we said, the Wigner function was the trace of rho with the symmetric delta function. I could do that for any operator and just say this is the, what's called Weyl symbol. It's got this pi in it, but never mind. It's got to be somewhere because there's these damn pi's in the integrals. So let's look at an arbitrary, so firstly, the Wigner function of alpha is 1 over pi right? It's equal to 1 over pi times the Weyl symbol for rho. Okay, yes? Yes, there is. Thank you. Very good. Pay attention. All right. So the Wigner function is the Weyl symbol with this pi. All right. With that said, let's look at the. I could say the following thing. Firstly, if I look at rho, I can vectorize it in the superoperator notation, and then write that in terms of insert the complete set of delta functions. Can I get that, right? And this is then equal to the Wigner function weighted by the delta functions. Okay, or in terms of going back to operator land, it says that the Wigner function tells me how to represent the state as a superposition of delta functions, symmetric delta functions. Moreover, if I look at the inner product between any two operators, well, maybe the first thing I want to do is let's look at the expected value of some observable that is equal to the trace of A with rho, right? But there's the trace of A with rho is the inner product of rho with A in superoperator land. Okay? And that, given this and the fact that this is all Hermitian, is equal to the integral or if I wanted to write it in terms of x and p, I'd have the Wigner function, the Weyl symbol as a function of x and p. Let's just absorb what this means for a moment because it's important. This is a quantum mechanical average value. The quantum mechanical average value, we have some formalism, blah-de-blah, the trace with the density operator. But if I didn't know better, and I just said there's some statistical distribution over x and p, and I want to know what is the average value of this operator that lives on this phase space, I would just average the thing that I want to know over the probability distribution. So this looks like classical StatMech, the Liouville formulation of statistical physics, where there's some probability distribution on phase space, and I have, you know, energy or angular momentum or something I want to know, and I would just take the average of it. Okay?
Step 2x plus.
Because, you know, because what my brain sees and what I don't know when it sees something else. Does that make sense? It's kind of interesting, right? It's saying that the Wigner, Herbert Weyl also formulated this at the same time, so then the Wigner-Weyl representations is a kind of very close to classical mechanics formulation, except that this can be negative someplace, okay? More generally, the inner product between two operators is equal to which is this, for an arbitrary operator, it would look like that. That's the two Weyl symbols, the Weyl symbol for B and the Weyl symbol for A, which need not be positive if A is not a Hermitian operator. If A is a Hermitian operator, then the Weyl symbol is a real number. So what is the trace of rho squared? Well, in that case, it's the Weyl symbol for rho squared, right? Because the Weyl symbol is positive in this case. but the Weyl symbol over pi is the Wigner function. So this is pi times the Wigner function squared, which, as we said, is actually less than or equal to 1. So that's a condition on the Wigner function. Yes?
So are we going to talk about how the uncertainty condition is imposed?
I mean, it's imposed here. If you want to have something, I mean, the uncertainty principle will constrain if the thing has a certain area under the curve, positive, and the square of that has this constraint, there's only so much you can squeeze it together. Yeah?
So, am I reading it right that so this kind of means that the Wigner function is bounded at like -1, 1?
There's some pi's in there.
If it's normally.
Yeah, if it's normalized.
Yeah.
So we'll get to that in a moment. Right. Now, as I was writing down over here, I can also think about the displacement operators as a basis, okay? So there's a natural other representation in terms of the displacement operators, and that's related to what's known as the characteristic function. So the characteristic function, which we'll call chi, which is a function of beta and beta star, or just beta as we're going to see, is the Fourier transform of the Wigner function. Which way did it go? Beta, alpha star, beta?
Beta first.
Beta first.
Yes.
Thank you, John. The best thing ever. Times the Wigner function. That's the characteristic function. And the Wigner function is the inverse Fourier transform of the characteristic function. Now, why is it called the characteristic function? It's called the characteristic function. The characteristic function is a well-known thing in statistics. I always like to say it's well known to those who know it well. In statistics, classical statistics, the characteristic function is the moment generating function. So let's say that I have some probability density over the real line. Okay, x is a real number. And I have some probability density. I could define a characteristic function, chi, which is just going to be equal to the Fourier transform of the probability density. Okay? And just make that definition. Why would I do that? The reason I do that is because the exponential is such a nice function that I can take derivatives of it and find moments of the distribution.
You can also take the log and look at the derivatives of the log and get your cumulants.
I can get cumulants. That's nice too. We won't go there yet. So what I mean by that, if I look at the, say, the derivative with respect to k m times, let me divide that by minus I to the power m of the characteristic function, and I evaluate that at the origin of the characteristic function, well, I just take the derivative of this km times, that'll just bring down minus I times km times. And so this is equal to, integral, this should be an integral over x, pardon me. This is the Fourier transform. X to the m of x. Everyone agree with that? So that is just the average value of x to the m. This is the mth moment. So the characteristic function is a useful function to have because it allows me to find the moments of the distribution, and as Cole said, I can think about the cumulants as well, by just looking at its derivatives at the origin. And of course, if it's an analytic function, then its derivatives of the origin define it everywhere through a Taylor series expansion. So that's just to say that the moments of the distribution completely define the distribution, and those moments are the derivatives of the Fourier or Laplace transform, if you want to deal with the i's. Okay, so that's where this is defined. And it's also useful in the quantum case, and for that I need to go back and say something that I forgot to say. So, let's say I look at some expectation value, okay? So for example, if I look at a dagger, a sim, that is a half. I have to symmetrize, put all permutations of A and A dagger, okay? Because of this thing with the symmetrized alpha function, what this equals is I can just replace every A dagger with an alpha star and every A with an alpha and average over the Wigner function. So it's a way of me calculating these correlation functions. It's because this thing was traced with the symmetric delta function. Okay? We'll kind of get into this a little bit more deeply today and next time, but this is a fact. What this means is that if we look at the definition of the characteristic function as the Fourier transform of the probability, the quasi-probability distribution, the moments of the distribution are found as the derivatives of the characteristic function at the origin, just like this. There's a symmetrically ordered correlation functions, but that's what they are. So if I look at the derivative of this thing, and now I'll put in the beta star with respect to beta, let's see, what do I want to do this? I want to do this n times, and I want to do this guy m times, and then evaluate that at beta equals 0. I get alpha star to the n, no, alpha to the alpha star to the, this doesn't really matter. What did I do? This is alpha star to the n, alpha to the m. Which is 1 over pi times so one of the things that's nice about the characteristic function is it allows me to calculate these correlation functions. The correlation functions are the moments of the distribution.
So when you say it allows me to calculate, you're assuming that your Wigner function has a good closed form and characteristic function has a good closed form, right?
Yeah, I mean, I need to calculate this thing. If I can calculate it, then I can do this. Yeah. Uh-huh.
So it's been a while since I taught statistics.
Yeah.
So that kind of correlation there.
Yeah.
How do we then put that to use? Like, why is it?
Yeah, so it's a good question. Well, we'll come back to this. We've seen things like this in the past in related to, say, photon counting, right? So these correlation functions are going to be related to things that we might want to measure about the light. We might want to look at something about their photon statistics or their statistics in terms of homodyne measurements. So these correlation functions are related to things we might want to measure. And that will, tell us more about how we think about those measurement outcomes as describable from a classical statistical theory or not. Okay, so now I want to come to some examples. We'll get there, and then that's probably all we're going to get to today. So, examples. Let's say we have a coherent state. Now, how are we going to calculate the Wigner function? Well, there's lots of ways to do it. We'll see some of them in homework, but kind of the most straightforward way is to first calculate the characteristic function and then take the inverse Fourier transform. So one strategy is find the characteristic function. The characteristic function, I should have said over here, I mean, it was implied, but I didn't write it out. The characteristic function is equal to 1 over pi, the trace of rho with the displacement. It's the Fourier transform of the delta function, right? So this is equal to 1 over pi, the trace of alpha naught with rho. With the displacement operator. Which is equal to that. So the characteristic function is the expected value of the displacement operator as a function of beta with the pi there, because God knows why. All right? So, how are you going to calculate that? Well, you have to remind yourself about some things about displacements and so forth. and I'm not gonna do that here. But I wanted to, cheat. You're gonna have to remind yourself I'm too lazy. Let me look at what I wanna say. Yeah. So, there's a lot of different ways to do this. Let me just remind you of some tricks, because I think it's good to see some of the tricks of the trade. There's lots of ways to do this, but this is probably the easiest thing to do. We know how the annihilation operator acts on alpha naught to the right, and how, so it's good. So if we remember, this thing is the exponential that looks like this. But I can write this in so-called normally ordered form using Baker-Campbell-Hausdorff. That one I remember, because we use it all the time. And now, when I plug that in, I've separated out the A's and A daggers, and I can just operate this on that, and that replaces this with its eigenvalue alpha naught, and this with its eigenvalue alpha naught star. So this is equal to 1 over pi e to the minus beta squared over 2 beta alpha star alpha naught star minus beta star alpha naught. Right? Because when A acts on that, I get alpha naught. Okay? So, how do I find the Wigner function? I have the characteristic function. Here's an example, Chauvin, where it's a nice closed form. I found it. Okay, it's an example. What kind of function is this, by the way, as a function of beta? It's a Gaussian, right? What is the Wigner function? How do I find it? I take the inverse Fourier transform. Which is 1 over pi squared e to the minus beta squared, and then I have e to the beta alpha minus alpha naught star minus beta star alpha minus alpha naught. Okay. So this is an example of a Gaussian integral, one that you will have practiced with in homework. And the answer is 2 over pi e to the minus alpha naught squared. There's a 2 up there. And if I write this in terms of the quadratures, this is then, if I write the function as a function of x and p, which is equal to a half w alpha equals x plus ip over root 2 for the normalization, then this is equal to 1 over pi e to the minus x naught squared minus p naught squared. This is the Wigner function of coherent state. Where alpha naught is x naught plus ip naught Is this what makes sense? Well, firstly, this is a Gaussian on the phase plane. It has a mean value which are x naught and p naught, right? So the average of x is x naught. Just like I would have, I mean, you can look at it. And the average of p is p naught. What is the variance or the uncertainty in x or p? Can you read it off from here?
Certificate factor 1/2 and then a half of it.
Right. Everyone, this is something I say every time, should memorize the formula for a Gaussian. You should know it by heart. You should know that if I have some probability distribution as a function of x, it's 1 over the square root of 2 pi sigma squared e to the minus x minus average x over 2 sigma squared, where sigma is the uncertainty in x.
There's a square.
Yes.
Everyone should know it.
But you better know that. So when you look at this, this is a probability distribution over 2 things, but separable. So it's a probability distribution of x. It's 2 Gaussians, one for x, one for p. And it's 2 times sigma squared, which means sigma squared is a half, right? So this is 1 over root 2. So it's correct. And when we draw this little circle here, what we're really drawing is the variance, the 1 over the variance of the Gaussian that's sticking out of the board. So when we drew this picture of a distribution with fluctuations in x and p, it's exactly these fluctuations. This of course is everywhere positive. It's a Gaussian, as was alluded to earlier. The coherent state is an example of a Gaussian state. It's a pure state. It's Gaussian, and in some sense, classical, that we'll emphasize more next time. More generally, if this were, as we're going to show in your homework, some squeeze state, which wasn't necessarily a coherent state, but was a minimum uncertainty state with some variance some way or another, that would be a Gaussian that would look exactly like this, but it would have a 2 sigma x squared and a 2 sigma p squared, which would be related to the Gaussian, would still be Gaussian. Okay.
So the point is, squeeze state
Is a Gaussian state.
it's classical from a Wigner function.
That's right. And what that means is that if I make any measurement of homodyne, which is one of the quadratures, it's perfectly statistically described in terms of a classical statistical problem from the point of view of homodyne and all the statistics, but not if I looked at photon counting. I can get Sub-Poissonian statistics. So it depends what I measure. Let's do another example. Let's look at a Fock state. For a Fock state, again, I can look at the characteristic function as the expectation value of the displacement operator. Which we did for homework, and it's equal to 1 over pi to the minus beta squared over 2 times a Laguerre polynomial. Two arguments or two. It's a calculation you will remind yourself of in homework. Okay?
Homework reminders in this lecture.
It's a lot of homework.
This homework is.
You're filling in all the gaps.
I remember.
So when we do the inverse Fourier transform of this, what we find is that this is 2 times minus 1 to the n over pi e to the minus 2 alpha squared, Wigner polynomial for alpha squared, which means the Wigner function as a function of x and p is equal to 1 over n minus 1 to the n e to the x squared plus p squared, the Wigner polynomial for x squared. P squared.
Does the Wigner polynomial take negative values?
It does. This also takes negative values.
Alright.
Yeah. So firstly, does this agree with what we expect for the vacuum? As n equals 0, that's 1, and I get back the Gaussian centered at the origin. But for n not equal to 0, this thing is non-Gaussian. Okay? For n greater than equal to 1, this is a non-Gaussian state. And every non-Gaussian pure state is negative. If I look at this function, what I see as it's, as expected, rotationally symmetric in phase space, as it must be, because the Fock state doesn't change when I rotate, because the generator of rotation is the number operator, right? So it's rotationally symmetric. If I look at this as a function of the distance, the radial distance in phase space, what I see is something that kind of looks like this for n equals 1, which has at the origin here, it's minus 1 over pi. In fact, the Wigner function, this Wigner function has this property, and this comes to the question that was asked earlier about the bounds on the Wigner function. This is true for this function, and it's true for all Wigner functions. It's hard to prove this. I don't know how to do it. I haven't done it in God knows how long. But this is true. The Wigner function is bounded between these numbers, or minus 1 over pi and pi in this normalization. Now, I want to just show you something on, before we quit, on the screen here, which is the home page of our website. And what the heck does it mean? You might have been wondering. Maybe you always knew. Here we are. USB-C. All right. Okay. So this was taken from a paper, from an old paper from Philippe Grandier's, where what's being shown here is the Wigner function for 4 different states. Okay, instead of x and p, it's q and p, but never mind. For a coherent state, a squeeze state, a single photon Fock state, and a so-called Schrodinger cat state. And what's being shown in those shadows are the marginal distributions, which is what you get when you integrate over the other direction. So if I integrate over Q, I get the marginal in P. If I integrate over P, I get the marginal in Q. Okay? So the shadows are the square of the wave function in position or momentum. Whereas the thing that's in 2D is the Wigner function. So what we see here for the coherent state is no matter what the marginal is, it's the same. And I see the vacuum fluctuations that are Gaussian fluctuations in the quadratures. For the squeeze state, I see different, this guy is squeezed in P and unsqueezed in X. This state is the first excited state of the harmonic oscillator, n equals 1 Fock state. In phase space, classically, it would just live on an energy surface that would be, have 1 unit of energy, whatever that is, h bar omega, would be a circle. But what we see is this deep negative dip here. Now, we kind of know it has to be there because if we thought about the first excited state of the harmonic oscillator, it has a node. It's got to be 0 right at the origin. The only way you can marginalize something which has something here is if something is negative the other way. And these are the Hermite polynomials times the Gauss, the first Hermite polynomial, not the Laguerre. There's Laguerre, believe everything's a hypergeometric function, whatever. But, that's what's being shown here. What about this state? That's really neat. This state is a superposition of 2 coherent states, which are superposed, they're separated in position. So it's like 2 Gaussian wave packets, one localized here and the other in here. Well, what's the Fourier transform of that, the momentum space wave function of something which is a superposition of here and there? It's like a particle going through 2 slits, right? Either it's in this slit in that one, but it's in superposition. And the Fourier transform of that is the far field diffraction pattern, which has interference fringes. So the momentum space wave function of the superposition of 2 is the double slit diffraction pattern, whose frequency depends on the separation, right? The more separated the 2 slits are, the faster the fringes are in the Fourier plane. And this is like the alive or dead cat, and these things are what's sometimes called the whiskers of the cat. This is the non-classical nature of the superposition. If these things were 0 and I projected on, I wouldn't see the interference fringes. I would just see the marginal would say, well, it's got some spread in momentum because I had it localized, but the interference between here or there is reflected in this negativity of the Wigner function. It's worth thinking about these things, how it all comes together. The X and the P and the energy plane, the phase plane, all at the same time. Very good. We'll quit there. Take up questions offline.